Hello, everyone. My name is Carl Duffy, and I will present Dodary, a KVSSD-based KV store. This work was done in conjunction with my colleagues at Seoul National University and Adju University. The fundamental issue we face is if we want to store a key value pair, where do we put it on the disk and how do we find it later, considering block SSDs just index the data with some logical block addresses. They don't know what a key value pair is. One way we can do this is through an LSM tree. And in LSM trees, we store data on the disk in levels of increasing size, and these levels contain sorted ranges of key value pairs. We have an in-memory component that is periodically flushed to the highest level, what we call level 0, and later, when level 0 gets too big, the values are merged inside and then flushed to the overlapping ranges in level 1. And this process repeats down the tree as time goes on. Later, when we want to find a key value pair, we'll search the memory component first, then search down the levels until we find the pair we want. Another way we can find key value data is in B+ trees, where typically we'll store the key value data we want in the leaves and then just store the locations of the leaves in the inner nodes. But if we don't have enough space in memory to store all the leaf nodes, leaves might exist on the disk, and when we want to update them, we have to read them into the host, modify them, and then write them back. Likewise, when we want to read the leaf, we have to read it into the host from the disk. Both of these structures work very well, but both have performance penalties. The LSM tree will have high read and write amplification for the reading, merging, and rewriting process as data gets pushed down the tree. And the B+ tree's write throughput will be hampered because when we want to update an index node that's not in the memory, we have to read it in, update it, and then read it, and then write it back. So we have a read, modify, write instead of a pure read path for the index nodes. So one possible solution to these problems is key value SSDs. And the issue is that the block interface doesn't know what a key value pair is. So we have to maintain these indexes ourselves and to index data on the disk. But key value SSDs, they ask, what if the disk itself could index the data and then we could just store and retrieve through key value pairs, and the index would be in the disk itself instead of us needing to maintain it. As a brief overview of how the KVSSD we test in this work works, the hardware itself is identical to a block SSD, an NVMe block SSD, just the firmware is flashed to provide the key value interface. And key value pairs inside the KVSSD are indexed in a hash table. And how it works as a high-level overview is that we place a request on a shard in the hash table, for example, a store request for my key, my value, and then later this shard will be merged into a global hash table and the data will be written to flash. At the same time, the key value SSD maintains what we call iterator buckets, where keys that share the same 4-byte prefix will be written elsewhere to a bucket so we can scan keys belonging to that prefix later. The issue is that currently available KVSSDs provide only basic functionality. So we have an in-place store, a get, delete, and the iterate. But the iterate at the moment, it's too slow for a general range query function. If we want stuff like transactions and snapshots, it requires us to write data out of place. And when we write data out of place, it implies that we're not writing it to the original key value pair. We need to write it to some other key because we don't want to overwrite the key value pair that's already there. So even if we use a key value SSD, if we want something other than simple key value storage, we still might need an index in the host to find this out of place data. So in this work, we look at the B+ tree through the lens of a KVSSD or the key value interface. And again, generally, if we want to update the index node of a B+ tree, but it's not in memory, we have to read it into the host first, update it, and then write it back. One scheme we could imagine is if we want to avoid this problem, what if when we wanted to update a node, we just blindly wrote the updates to the disk and then later somehow collected all these updates and built the node in memory when we wanted to service a read. That way we could have high write throughput. But the issue with this scheme is that if we write these updates to disk blindly without reading the node into the host first, how would we find these updates later on the block SSD? And the result is that we just would need another index to find all of these updates somewhere. So we have doubled the index persistence penalty in the pursuit of higher write throughput for the B+ tree. So given that thought, what if the disk could just find the updates for us? So we could blindly persist updates to index nodes. And if the disk had some sort of functionality where it could find them for us, we could then collect them when we want to read the node and build the node in memory. So in this case, we can try to use the key value SSD. And when we want to update an index node, we just blindly persist the update and then collect the key value pairs later using the key value interface, assuming we know how the keys are formed. And in this work, we introduced a scheme like this called the oak tree. So it's the out of order append only KVSSD B+ tree. The in-memory representation of the oak tree is the same as a typical B+ tree, but how we persist and read data differs. Each index node has a special key on the key value SSD, and we persist updates to special keys without first reading the index nodes into the host memory. So as an example, we have a B+ tree, or the memory portion of the oak tree in memory, but node N6 isn't in memory. We didn't have enough memory to store it, but we want to update node N6 with the delta of G. What we do is we read a counter for each index node in memory, and that counter will tell us how many outstanding updates are already on the disk for this index node. In this case, N6 has 2 updates already on the disk. We have the key value pair node N60, which has H delta, and we have the key value pair node N61, which has a second delta of H. So we want to update N6 with the delta of G, and we already know that there are 2 updates to N6 on the KVSSD. So without reading N6 into the host first, we write this update blindly to the KVSSD with the key node N62, the next update in line, with the delta of G. Next, when we actually need to service a read from N6, we need the index node in memory. First, we check the in-memory counter for N6, and we see we have 3 updates outstanding on the key value SSD. Now, because we already know how the keys are formed, what we can do is just read all of these updates asynchronously in parallel, collect them, and then merge them in memory to create the index node N6. So we read N60, N61, and N62 using the key value interface, merged them, and then created the node in memory. So we have updated N6 without reading it back into the host memory. And then when we've actually needed to read it, we've just collected all the updates without needing to persist another index because we have a key value SSD underneath. With the oak tree at the center, we make a key value store called Dotery. And in Dotery, we don't persist key value pairs to their original key on the key value SSD. Instead, we write them with an ascending version number. And we do this to support out-of-place updates for transactions and snapshots. To find these user key to the actual key on the key value SSD mappings, we have the oak tree as the center of the store. High-level overview of a store in Dotery is that first, the user might want to store my key, my value. And again, my key won't be written to the KVSSD as my key. Instead, it will get some it will get some version number, the latest version number available. That will be the key on the key value SSD. First, these mappings from the user key to the version number on the key value SSD will be stored in what we call the index update buffer. And then later, when those updates in the index update buffer are finalized, so if the transaction they belong to commits, for example, they're then flushed to the oak tree. And then the oak tree is updated with these user key to key value SSD key mappings. And then later, when we want to read a key value pair, we check the index update buffer first. And if there's a miss there, we check the oak tree. Other things we get from the key value interface are, first, we can avoid compaction because with the key value interface, we can just tell the key value SSD to delete stale data. So when something gets overwritten in Dotery and the old value isn't part of a snapshot, we just send a delete command to the KVSSD to drop the data instead of traditional compaction. The second is that we can get very fast recovery because in block device KV stores, when we're recovering, for example, the log generally, we have to read a block and check what's inside. So what key value pairs are there? And do the key value pairs in this block spill to the next block? Which kind of slows down recovery, even on really, really fast devices. But in Dotery, Recovery is recovering the index update buffer because those updates are not finalized. And what we do is, because the keys are just ascending version numbers and each key represents a separate key value pair, we just asynchronously in parallel read all of the keys since the last index update buffer flush. So we can do that at the peak bandwidth of the device, just read everything blindly and then continue. So recovery can be very, very fast. In the paper, we have comparisons to other index types, more details about the KVSSD and its performance, more internals about the Oaktree, and more details about Dotaree's design and its KVSSD specifics. We evaluated Dotaree against some modern block device key value stores and the key value SSD itself. And it's important to note again, the evaluations are carried out on the same disk. It's just flashed with a different firmware to provide a different interface. So it's the exact same hardware. Most of the tests are done on the YCSB workloads, and we studied the performance of the Oaktree too. So to set the scene for the KVSSD and block device raw performance, we can look at the IOPS and latency at different value sizes. And in general, the KVSSD far underperforms the block SSD because it pays penalties for maintaining its iterator function, persisting its own hash table, and placing variable size key value data instead of just fixed size blocks like the block SSD. For the Oaktree, to bound the amount of updates and bound the read time of index nodes, we have this setting called max logs. And it's, for example, max logs value of 4 means at most we can have 4 updates for this index node on the disk. So varying max logs, we look at the read latency when it increases. And at a small max logs value, for example, 4, the read latency of an index node is quite low. And while it gracefully increases as max logs gets bigger, we run into a problem when max logs gets too large. And it's that most of the time starts to get spent actually submitting commands to the key value SSD instead of actually reading the node data or reading the deltas from the key value pairs. So we use this as one data point in a larger argument for batch commands on the key value SSD, where when we want to handle a lot of smaller key value pairs, we just send all the commands in one batch to the disk, freeing up a lot of slots in the queue. If we look at the YCSB uniform results for 1 kilobyte key value pairs, we see that even though the KVSSD itself is much slower than the block SSD, we can still outperform the block device key value stores. And it's because persisting the Oaktree is such a lightweight operation, we're just blindly writing updates most of the time. And second, because of the key value interface, we're avoiding compaction. We can just delete stale data instead of reading and rewriting blocks like in the block device stores. And where Dotaree might perform the same or worse than the other stores, we still win on read latency in the presence of writes because the disk is doing so much less work, and because of the low Oaktree overhead and the avoidance of compaction thanks to the key value interface. Finally, even though Dotaree can perform very well, where it performs poorly is small values, and there are 2 reasons. The first is that for the KVSSD we test, and maybe for future hash table KVSSDs too, to bound the size of this hash table in the device, small values are padded to a larger size, in our case 1 kilobyte. So for example, if we write 100 byte values in the KVSSD that we test, they will be padded to 1 kilobyte. So there's over 10 times space amplification just for small values. The second thing is that because we're writing key value pairs separately to the key value SSD, we can't group them into one larger write unit like block device KV stores do in group comment mechanisms. So they'll group a lot of smaller KV pairs into a block and write it to the disk. But in our case, we're sending a new command for each small key value pair write, which really, really reduces the write throughput compared to the block stores. So Dotaree and the KVSSD, they can't compete for the small value performance right now. To conclude, we look at this B plus tree read modify write problem through the lens of the key value interface, and we introduce the Oaktree, a B plus tree built upon the key value SSD, and Dotaree, a key value store built on this Oaktree. And even though the key value SSD itself can always significantly underperforms the block SSD, Dotaree can really outperform the block device KV stores because of the low index maintenance overhead of the Oaktree and the avoidance of compaction because of the key value interface. Thank you.